Hi, my name is Dylan Zeller, and today we're going to be doing proof by induction for the sum of 2 to the k from k equals 1 to n. And we're going to prove that it equals 2 to the n plus 1 minus 2. This is my third presentation for CS520. So the first question is, how do we do an inductive proof? Well, there are two steps. The first step is to prove the base case. Here we'll prove that an input is equal to the solution. In the second step, the inductive step, we're going to prove that the statement S of k implies S of k plus 1. So what does this mean? That means after the statement k is proved, which we'll use the base case, we can prove that the next iteration in the sum, S of k plus 1, will also be true. For an inductive proof, you have to assume that S of k is always true. If every statement implies the next one, all statements will be true. This means if you have 5 proofs, S1, S2, S3, S4, and S5, if S1 is true, it will imply S2, and that will imply S3, and that will imply S4, and that will imply S5. So first, let's prove the base case. Here at the top, we have our solution. For the base case, you have to pick a value to see if the two sides are equal. In this case, we're going to use 1. It's a very easy value. So right here, we've plugged in the values for this equation. 2 to the 1 equals 2 to the 1 plus 1 minus 2. As we go down, we simplify the equation more and more. So 2 equals 2 squared minus 2, then 2 equals 4 minus 2, and 2 equals 2. So now that we've proven the base case, we can move on to the next step. So this is the inductive step. Here, we're going to prove that the statement S of k implies S of k plus 1. So this is the inductive hypothesis. For this, we have to assume S of k is true. So here you can see we have S of k plus 1. That is the sum of 2 to the k from k equals 1 to n plus 1. And that evaluates to the previous sum, which is the sum of 2 to the k from k equals 1 to n, and the next element that we've added on, which is 2 to the n plus 1. In order to prove this by induction, we have to evaluate and simplify the proof. So here we can simplify the previous sum, which we looked at on the previous slide, to 2 to the n plus 1 minus 2. Now, we still have the other term at the end. From here, we can simplify. We can combine the like terms with this one on the end and this one on the front, which will make it 2 times 2 to the n plus 1 minus 2. When a number with an exponent is multiplied by the same number as its base, you can add 1 to the exponent. So here at the bottom, you can see we have 2 to the n plus 1 minus 2. This is the same as our previous solution, but for the next sum. So let's do a quick. So now we can do a quick recap. We proved that the base case, which we chose 1 as the value for, was true for the sum of 2 to the k from k equals 1 to n equals 2 to the n plus 1 minus 2. The second part was to prove the inductive step. We proved that the statement S of k implies S of k plus 1. So on the right here, we can see S of k, the original sum, which is 2 to the k from k equals 1 to n equals 2 to the n plus 1 minus 2. While on the bottom here, we have S of k plus 1, which we proved in the last slide. This is the sum of 2 to the k from k equals 1 to n plus 1, and that equals 2 to the n plus 1 minus 2. You can see here that the n in the top one has been replaced with an n plus 1 in the bottom one. So we've learned that assuming S of k is true, S of k plus 1 is always true. So here are my resources. Thank you for watching.